Hello, my name is Jackson, a second year mechatronics engineering student.
And I'm Kai Mitchell, a third year CNI engineering and IT student.
We have been working as a team to complete the electrical case study for MATLAB Project B. This presentation will outline our process of modifying existing MATLAB code given as part of a case study on RLC circuits. We will first discuss the background theory of RLC circuits and then the existing code given as part of the case study. We will then explain our modifications to the given code to include temperature effects on the various components. Finally, conclusions will be drawn on the optimal temperature ranges for the RLC circuit. RLC circuits are common electrical circuits with components of an inductor, a capacitor, and a resistor. These circuits are commonly used in applications such as TV receivers to achieve an appreciable signal voltage at different resonances. RLC circuits have varying behavior depending on the values and orientation of the circuit components. The circuit can have a transient response when it transitions from one steady state to another, a resonant response when its impedance reaches a minimum resulting in a maximum current flow, or a damping response when the circuit is dissipating energy over time.
The case study uses system equations. The system equations used are the voltage across the resistor is the sum of the voltage across the inductor and the capacitor, since they're connected in parallel. Using Kirchhoff's law at the node, we can express the current from the source as the sum of the current through the inductor and the current through the resistor. This can be rewritten to show the relationship between the source current and the voltages across the components, leading up to the second order differential equations necessary for further analysis. Deriving the system equations includes taking the derivative of both sides of our rewritten equations. The result is a second order differential equation for the current through the inductor and another for the voltage across the resistor. These equations are then implemented in MATLAB using these functions to define the system of differential equations. The main MATLAB code involves a function to represent the right-hand side of the differential equation and additional functions to model the source current and its derivative. The MATLAB code uses these functions to compute the behavior of the RLC circuit over time.
The current code in MATLAB utilizes the ODE equation and the given values of the circuit to compute the voltage and current across the various components. Currently, the values of RLC are hard-coded at the top of the RLC script and are manipulated using the ODE equations and the ODE45 function to calculate the current across the inductor. Using a combination of Ohm's law, KCL and KVL, the voltages across the capacitor and resistor, VR and VC, and the current across the resistor, IR, can be found. By then plotting these values against time using the plot function in MATLAB, graphs can be obtained to visualize the voltage and current oscillations. The current case study used subplots to plot all the voltage and current graphs next to one another. VR, VL, and VC were on one plot, and IL and IR were on another. Another plot was made to show the frequency response by measuring the current across the resistor at varying frequencies, and then finding the ratio of the input voltage to the output voltage. These values were then entered into a list for X and Y, and then using the semilog function were plotted onto a graph.
The sensitivity of an RLC circuit's response to temperature is tied to the characteristic of the materials comprising its components. Each material exhibits a unique temperature coefficient, TCR, which is a measure of how its resistivity varies with the temperature. This phenomenon arises from the movement of electrons within the material structure. As the temperature fluctuates, the TRC of each component material comes into play, influencing the resistance of resistors, the inductance of inductors, and the capacitance of capacitors. These variations in the components' values directly translates to changes in the circuit behavior. Consequences of temperature-induced variations in the components' values extend beyond the numerical shifts. These manifest in the alterations in the circuit's performance characteristics. For instance, changes in the impedance can impact signal transmission efficiency, while shifts in resonance behaviors may affect filter or tuning applications. When dealing with the RLC circuits, the temperature can affect the resistance, inductance, and capacitance of its components by using the coefficient of resistance, the TCR equation. The change of RLC values can be recalculated based on a reference and final temperature. This equation applies not only to the resistors, but to the inductors and capacitors with a simple change of variables. Starting at a reference temperature of 20 degrees Celsius, we select the temperature coefficients based on the materials commonly used in the components. So we went with a copper round resistor with a TCR value of 0.004 parts per Celsius, a wire round air core inductor with a TCR value of 0.000125 parts per Celsius, and a ceramic base capacitor with a TCR value of neg 0.00003 parts per Celsius. They each have their own optimal temperature range, with the inductor being the minimum optimal temperature range of negative 40 degrees Celsius to 85 degrees Celsius. These TCR values are crucial for temperature compensation strategies, ensuring stable circuit performance across varying temperatures.
The initial code underwent significant improvements, primarily focusing on the modularization, temperature implementation, result visualization, and user interface. The code was further modularized by splitting the code into separate script files in the MATLAB project, mainly a graphing function and a temperature function. These functions were then called within a main script to enhance the readability and debugging of the project. The new temperature function was introduced to incorporate temperature effects into the system by using the previously discussed formulas for the RLC values were then recalculated based on temperatures. The new results were then graphed in a separate subplot and separated via menus to maintain readability and provide easier comparisons. To make use of this menu system, a GUI was developed using the MATLAB UI app, enabling users to input their own component values and temperature-resistant coefficients, as well as set the temperature changes directly. The main addition to the given code was a temperature function called tempConstant. This function adjusts RLC values based on the temperature changes. The function takes the temperature coefficient, the TRC values, and the reference temperature, Tref, of a resistor, inductor, and capacitor, provided by the user, and then uses the previously discussed equation to recalculate the values. Because of the 3D nature of the graphs, temperature is passed to the function and the new value of RLC is calculated for each temperature difference.
The graphing tab 1 is a function that generates a voltage across resistor, voltage across inductor, and voltage across capacitor versus time graph, and a current across inductor and a current across resistor versus time graph from the case study. In the MATLAB app, the generate graph button push function activates on a button push. This function calls the graphing tab 1 function with the inputted values defined in the case study to generate a replica of the case study graphs. Then the temperature constant function is called, finding the temperature affected RCL values. The graphing tab 1 function is then called again with the temperature defective values to generate a temperature affected graph for comparison. On the first tab of the app, based on the inputted values, the app outputs a voltage across resistor, voltage across inductor, and voltage across capacitance versus time graph, and a current over inductor and current over resistor versus time graph without the affected temperature values, and two more with the effective temperature values. When the temperature is increased, the voltage graphs have a higher positive peak value and a lower negative peak value, and the current graphs have high peak values for both negative and positive.
Graphing tab 2 is a function that generates the voltage across the resistor, inductor, and capacitor versus temperature versus time graph, and a current across the inductor and resistor versus temperature versus time graph. Each Y value has its own matrix. For example, the voltage across the resistor has a voltage across resistor values, and the temperature range, is the temperature range from negative 40 to 80 degrees Celsius. For each value in the temperature range, temperature-affected RCL values are generated with a temperature constant function. Then the values, voltage and current, are calculated and stored in their respective matrix. Then each matrix is graphed against time and temperature using the surf function. In the MATLAB app, the Generate Graph button push 2 function activates on a button push. The function calls graph tab 2 with inputted values to generate the 3D graphs. On the second tab, based on the inputted values, the app outputs are the voltage across a resistor, inductor, and capacitor versus temperature versus time 3D graph, and the current across an inductor and resistor versus time 3D graph. The colors for each value in the graphs are as follows. Voltage across the resistor is red, voltage across the inductor is green, and the voltage across the capacitor is blue. The current across the resistor is magenta, and the current across the capacitor is cyan. When the temperature is increased, the voltage graphs have a higher positive peak value and a lower negative peak value, and the current graphs have a higher peak values.
Graphing tab 3 is a function that generates the resonant frequency versus current over resistor versus current and then the initial current ratio graph. This function loops through the length of the array holding the omega values and then calculates the IR over I0 ratio and stores it in a new array corresponding to the same index. In the MATLAB app, the Generate Graph button free push function activates on a button push. The function calls a graphing tab 3 with the inputted values to generate a replica of the case study graphs. The temp const function is called again to create temperature affected graphs. In this tab, based on the inputted values, the app outputs a resonant frequency versus current over resistor over initial current ratio graph with and without the effect of temperature. It was observed that when temperature increased, the IR over I initial is lower at the same resonant frequency. Graphing tab 4 is a function that generates a frequency versus current over resistor versus initial current ratio versus temperature 3D graph. An array of temperatures in intervals of 5 between 40 to 85 is used. For each value in the omega array, temperature affected RC and L values are generated with the temp cos function. Then the value of initial current over resistor and current over an initial current is calculated and stored in the IR over I0 ratios matrix. Then the matrix is graphed against the omega frequency and temperature using the surf function in the MATLAB app. The Generate Graph button push 4 function activates on a button push. The function calls the graphing tab 4 with the inputted values to generate a 3D graph. Based on the inputted values on this tab, the app outputs are the resonant frequency versus current over resistor over initial current ratio versus temperature 3D graph. The trend of lowering IR over I0 as temperature increased was also observed in the graph.
As temperature fluctuates within electronic systems, the behavior of the components such as resistors, inductors, and capacitors can deviate from ideal performance, introducing errors in voltage and current measurements. This phenomenon occurs because variations in temperature excite the electrons within the materials, altering their conductivity and affecting their flow of current and voltage. It can be seen in the 3D graphs of both the voltage and current that as temperature increases, the voltage and current increase. While this is hard to identify because of the small TCR values chosen, this difference in values can still affect the operation of the circuit. To mitigate these temperature-related effects, careful selection of component materials and characteristics is crucial. By understanding the application and anticipated operating conditions of the circuit, engineers can tailor components to achieve optimal temperature coefficient of resistance values. In more complex circuits, engineers may implement temperature compensation circuits to counteract thermal effects. These circuits utilize various techniques such as feedback mechanisms and thermosistors to adjust component parameters dynamically, ensuring consistent performance across a wide temperature range. Thank you for listening.